Calculus of several variables. The topics I will be covering are mentioned in the description. Go through them. I will be following the book Advanced Engineering Mathematics Volume 1 by Chitaneja. Do practice example sums and exercises from it. It really helps. Partial differentiation. We all know that du by dx is the derivative of a function u with respect to x. Then del u by del x is the partial derivative of u with respect to x, also denoted by f subscript x. Del is lowercase delta. What matters is how you operate it. Let u be a function of three independent variables. Then we have three partial derivatives of the first order denoted by del u by del x, del u by del y, and del u by del z. Here del u by del x is obtained by differentiating u with respect to x, treating both y and z as constants. The same rule applies for both del u by del y and del u by del z. Hence for u equals to x square plus y square plus z square plus xy e to the power of x, the partial derivatives are as follows. Partial derivatives of second or higher order operate in almost the same way. The second order partial derivative for f is nothing but the first partial x derivative of the x partial derivative of f. And with the same pattern we can figure everything else out except the answer to life, which is 42. Homogeneous functions. A function of x and y is said to be a homogeneous function of order n if the degree of each of its term in x and y is equal to n. For example, this is a homogeneous function of order n, which means take any term and add the powers of x and y. If it is equal to n, then a function is homogeneous. This should apply to every term. Euler's theorem on homogeneous functions. If a function of x and y is a homogeneous function of order n in x and y, then x times the partial of f with respect to x and y times the partial with respect to y equals n times f. It is pretty much used to solve problems in engineering textbooks, like if u equals tan inverse of x cube plus y cube by x minus y, prove that x del u by del x plus y del u by del y is equal to sin 2u. Just equate z with tan u, make it homogeneous, cancel out x and take x square common from the numerator and solve. Total differentials. Totally. Consider a function of x and y, u. The total differential du is given by the sum of fx dx and fy dy. Similarly, for more than two independent variables, the total differential is so. Remember, fx is the partial with respect to x and fy is the partial with respect to y. By now you're probably thinking why? Why study partial derivatives? And what's up with Euler? Why complicate our lives even further? Well, consider this. You're working on the final equations of your time machine when your wife suddenly starts complaining that she has become a silicon widow. Your teenage daughter wants your credit card and your pet dog just peed on your favorite couch again. Also, to make things worse, you end up with a function you cannot solve and you completely lose it and decide to burn down your own house. Hence, to stop this, a bunch of really cool guys like Euler, Taylor, Maclaurin, Lagrange, etc. derived a bunch of methods so that you can find an approximate value to the differential functions and not commit genocide, but rather run naked on the street screaming Eureka with Archimedes because of your new time machine, or end up in a gas chamber because you only got it approximately right. The circle of life totally makes sense. Totally. Which reminds me, I got sidetracked talking about total differentials, and now that we know why it is used, we reach approximation by total differentials. We saw that the approximate change du corresponds to a small change dx in x and dy in y. Once these are calculated, we can use it to estimate errors in calculations. Hence, maximum absolute error is given by this. Remember, u is a function of x and y. The ratio mod df by mod f is the maximum relative error, and times 100 is the maximum percentage error. Taylor and Maclaurin series. They are just representations of a function as an infinite series. If f of x is continuously differentiable at x equals a, then f of x can be expanded by f of a plus first derivative of f of a times x minus a plus second derivative of f of a by 2 factorial times x minus a square and so on up to the required term. In short, Taylor's expansion is the summation of n derivative of a by n factorial times x minus e to the power n, where n ranges from 0 to infinity. The series is centered at a. If it is centered at 0, then it's called the Maclaurin series. So the function expands to f of 0 plus first derivative of f of 0 times x and so on. Generally, the summation of n derivative of f of 0 by n factorial times the power of n, where n ranges from 0 to infinity. For example, determine the Maclaurin series for f of x equals sin x. Keep this in mind. Find the first few derivatives of sin x. Since we have to find a Maclaurin series, evaluate them at f of 0. The values are so on. Substitute in the summation formula and expand. If we notice the pattern, we can continue the series. Observing the pattern, we can generally write sin x as the summation of negative 1 to the power n times x to the power 2n plus 1 by 2n plus 1 factorial, where n ranges from 0 to infinity. Negative 1 due to the alternating signs, 2n plus 1 factorial because of the continuous odd numbers in the denominator, and x raised to the power of 2n plus 1 due to the continuous odd powers of x. And there is your answer. Super, now let's look at it graphically. As you can see, when we increase the terms of our series for a cos x function, we keep getting closer to the function and eventually we are spot on. Another example. Determine the Taylor series expansion for the function f of x equals e to the power x. Solve it the same way you solve the Maclaurin series, only your a equals negative 1. Find a bunch of derivatives and substitute and find the pattern. Do remember the terms are counted as 0, 1, 2, 3 and so on. However, a function equals the Taylor's polynomial and a remainder. The remainder is nothing but the error between the actual function value and the estimate we found using Taylor's polynomial. The remainder is given by n plus 1th derivative of x by n plus 1 factorial times x minus e to the power n plus 1. The k is a bit of a brainer, but a couple of example sums from your textbooks will make it clear. Or you can watch the video Taylor's theorem with remainder by Bull Cleo 1. Link is in the description below. Maximum-minimum saddle point. Suppose that the first partial derivative of ab with respect to x equals 0 and with respect to y also equals 0, then keep this equation of d in mind. So if a, d is greater than 0 and the second partial with respect to x is also greater than 0, then we have a local minimum. B, if d is greater than 0 and the second partial with respect to x is less than 0, then we have a local maximum. If d is less than 0, then the point is neither a local minimum or a local maximum. We call it a saddle point. Example. We need to find the maximum and minimum values of the function x cubed plus y cubed minus 3axy where a is greater than 0. We have a function of x and y. We find fx, fxx, fxy, fy, fyy as per the requirement of the equation. To find the critical points, we equate fx and fy to 0. Therefore, x squared equals ay and y squared equals ax. With these, we find our critical points or the values of x and y to be 0, 0 and aa. These are your a and b. At 0, 0, the value of d is less than 0. Therefore, it is a saddle point. At aa, the value of d is greater than 0 and fxx is also greater than 0. Hence, aa is a point of local minima and the minimum values of the function is equal to negative a cubed. Lagrange's method. It is just a bunch of steps we follow to find the extremes of a function under the condition that the same function could be equated to 0. Might get a little confusing from now, but it will become clear when we take up an example, so bear with me. First, we construct an auxiliary function which equals to the original function plus lambda times the conditional function. Lambda is a Lagrange multiplier. Second, find the stationary points of f. For this, we partially differentiate it with respect to each of its variables and equate them with 0. Third, we have these equations as well. Pause the video and make sense out of them, because these equations help us find x, y and z. This will lead us to the extremes of a function as the question asks. Example, we need to find the maximum and minimum distances of a point A 3, 4, 12 from the sphere x squared plus y squared plus z squared equals 1. So phi x, y, z equals x squared plus y squared plus z squared minus 1, which equals 0. Let P be a point on the sphere. Therefore, its distance from A will be such. Just to simplify it, let's take the square of the distance and find its extremes. So the function equals to this. Our auxiliary function now becomes a function of x, y, z and lambda, which we can derive from the general formula. For extreme values, we do the second partial differential step and proceed to find the values of x, y and z in terms of lambda. Multiply this with x, this with y and this with z and add. We get the following equation. Since this is 1, it simplifies to this equation. Now substitute these values in the equation. We find lambda to be 12 or minus 14. Now get the values of x, y and z by substituting the value of lambda in the derived x, y and z equations. So at lambda equals 12, the point on the sphere is P 3 by 13, 4 by 13 and 12 by 13. and add lambda equals negative 14. The point on Q is minus 3 by 13, minus 4 by 13, and minus 12 by 13. So the distance AP is 12 and AQ is 14. 12 and 14 are your answers, your extremes, and that's that. You can find assignments on this chapter on this website. Remember that their database is updated frequently, so if you can't find something you're looking for today, you might find it tomorrow. All details are in the description of this video. Thanks for watching.